Hi, we are TripleTensor. I'm Aditya, along with Adit and Ameya, and this is a Sprint 1 demo for DarkFleet. Every year, thousands of commercial fishing vessels deliberately switch off their AIS transponders, which is a mandatory tracking system, to hide illegal, unreported, and unregulated activity. This is called going dark. The fish in protected zones transfer illegal catch at sea or evade sanctions. IUU fishing costs the global fishing economy an estimated 10 to 23 billion US dollars annually. So DarkFleet is an AI-powered intelligence system that detects these dark vessel events and classifies whether they are intentional or accidental, and risk scores them for maritime enforcement analysis. Our Sprint 1 goal was to deliver a working binary classifier as a proof of concept and to validate the full pipeline end to end. We hit that goal, and along the way, we made a critical data set discovery that fundamentally shapes Sprint 2. Let me walk you through it.
I'm Adit and I'll walk you through the system architecture. Four parallel work streams this sprint: data ingestion and EDA, the core gap detector and binary classifier pipeline, the fast API backend skeleton, which I built, and the React Leaflet analyst dashboard wireframe. The pipeline shows that left to right, raw IAS pings enter the gap detector, which flags open ocean disappearances over 6 hours. The feature engineer enriches each candidate within 15 contextual features. The XGBoost binary classifier predicts intentional suppression versus benign gaps, and the evaluation suite logs everything to clear ML for full reproducibility. The backend I built sits at the right end of this pipeline. The fast API service exposes the classifier to the dashboard over a tight REST API. Critically, this isn't notebook only work. Behind the notebooks, it's production ready quality Python source modules in a DarkFleet folder, 14 passing unit test in the test folder, and a complete documentation in docs folder. Aditya will walk you through the ML stages, and let me first cover the data. We are working with four open access data sources from Global Fishing Watch. The primary ground truth is the Welsh et al. 2022 dataset, over 55,000 confirmed IAS disabling events by commercial fishing vessels between 2017 and 19, published in Science Advances. These are our positive labels. Notice the data has real vessel identities, MMSI, flag state, vessel class, and dimensions. The spatial distribution clusters in the Northwest Pacific, West Africa, and South Atlantic, the world's heaviest fished open ocean regions. For negative examples, benign gaps, we used GWF's anonymized AIS training data, 7 flags split by gear type, totaling about 3.4 gigabytes. We almost used a global anchorages database with 166,000 port locations and a fishing effort grid at a zero point 0.1 degree resolution. One thing to flag: the Welsh data has real vessel identities. The anonymized negatives have none by design. The difference between the two datasets is the key to understanding the evaluation results Aditya will show you shortly. I will hand over to Ameya to now walk through the gap detection pipeline.
Hi, I'm Ameya, and I'll walk you through the gap detection stage. This is the core stage of the pipeline I was responsible for, and running it and end-to-end in our Docker environment. So for each cell in the AI's data, we sort pings by timestamps and compute inter-ping time data. So for any gap exceeding 6 hours, triggers a candidate. So two filters then removed benign gaps. The coastal filter discards gap starting within 50 nautical miles offshore. AI's coverage near coastlines is unreliable. The port filter discards gaps within 10 kilometers of any known anchorage. The vessel was likely just in port. The key technical decision was the spatial index, Baldry with a Habershine metric over 166,000 anchorage locations. Brute force nearest neighbor search over 166,000 points for every gap event and would be prohibitively slow. Boulder gives us complexity of overflow of n queries, fast enough to run the full dataset in seconds per byte. This is also the stage track as a DBC pipeline node, which I'll show you later. The two output is the two files. So the DarkFleet event candidates a CSV file with OpenOcean candidates and all gaps CSV file with with the full output, including many categories. Both feed into the next stage. So I'll hand back to Aditya for the feature engineering and classifier.
The feature engineering step takes raw gap events and builds a 16 feature vector for each one. We end up with 70,113 samples, about 55,000 positives from our dataset, and about 14,800 negatives from the benign gap output. The 16 features span 4 dimensions: the gap characteristics, duration and long duration, temporal context, hour of day encoded cyclically with sine and cosine, so midnight doesn't create an artificial discontinuity at the boundary, vessel identity, flag state risk score, vessel class, tonnage, and length, spatial context, distance from shore, proximity to anchorages, and fishing effort density at the event location. The classifier is XGBoost with a scale POS weight of 0.27 to handle the class imbalance. We choose XGBoost because it handles missing values natively. Critical here, since 21% of vessel metadata features NaN for the anonymized negatives, and because S-sharp values give us full feature level interpretability. This line logs every training run to clear ML automatically. That is hyperparameters, metrics, plots, model artifacts, everything reproducible from a single experiment ID. This is the feature importance plot from the trained model. The 3 bars on the left, flag state risk, vessel tonnage GT, vessel length M, have sharp gain values of 0.45, 0.3, and 0.26. The other 12 features, including gap duration, fishing effort density, and time of day, they contribute essentially 0 to every prediction. Now remember what I said during EDA. These 3 features are vessel identity metadata, and they are only populated for the positive class. The anonymized negatives here, NaN, for all 3 by design. The model learned one rule: if vessel metadata is not NaN, predict intentional suppression. If it is NaN, predict the benign. It's not intelligence about dark vessel behavior, but it's a data collection artifact. This is an experiment on cleared ML. So we have the F1 score, we have the precision recall, the ROC AUC, all exactly 1.0 on both validation and test sets. The confusion matrix, 0 false positives, 0 false negatives. Model files uploaded and versioned. The pipeline works perfectly. The data set doesn't. Let me show you how we are framing this. Here's the very critical information that we found. Our F1 score equals 1, which we would classify as a successful fast fail. We're not hiding from this result. We are leading with it. A fast fail means he surfaced a fundamental problem early before committing sprint to resources in the wrong direction. That's what good engineering looks like, frankly. The root cause, we have 3 contributing factors. First, vessel metadata asymmetry. Positives have it, the negatives don't. Second, easy negatives. Coastal and port gaps are spatially separated from open ocean positives by definition. So distance from shore alone separates the classes trivially. Third, no hard negatives. We have no open ocean benign events that are genuinely ambiguous for the model to learn from. Based on this, the sprint 2 fix is clear. We replace easy negatives with hard open ocean candidates from anonymized AIS training data, remove or resource the vessel metadata features, and implement a time-based train test split. So we train on 2017 and 2018 data, and we test on the 2019 data. We also need to fix a data leakage issue in the historical gap frequency feature. So an expected collected performance in F1 would be in the range of 0.75 to 0.85. which is exactly the sprint target under realistic conditions.
I am Udit and I handle the backend and front end this sprint. The fast API backend is the bridge between ML pipeline and the analyst dashboard. Here's the predict dark event endpoint, and this is what the front end will call when an analyst wants to classify a gap event. The request body is validated with a pydantic, so any malformed input gets rejected at the schema boundary before it touches the model. The key design decision Aditya and I aligned on was keeping features engineering server side. The client sends raw event attributes, that is the gap coordinates, timestamps, and vessel class, and the backend computes the 15 derived features before passing them to XGBoost. That keeps the front end thin and ensures the features logic is consistent for every consumer of the API, whether that's the dashboard, an analyst script, or a future mobile app. And if you can see here, this is the analyst dashboard wireframe that I designed for Scrum 29. The map is the centerpiece, and the dark events surface as markers. Analysts can click through the risk score and contributing features. This wireframe drives the React Leaflet implementation for Sprint 2, which will be made using TypeScript or React Native, depending on the feasibility of the app.
Hi, I'm Megan. So for this sprint, I have handled MLOps infrastructure this sprint. So the first thing which I did was the setup of the consistent environment for the whole team. So Docker Compose runs on two services, ML Workspace where Aditya runs training and API backend where Adit develops the API service. So any team member when clones the repo and runs Docker Compose YAML file, they get identical Python versions and dependencies. So no one faces the issues of environmental environment drift or those on my machine issues. The next thing which I did was the data versioning. For this, I had set up a DVC to manage the pipeline as a directed cyclic graph. So for each stage, like gap detection, feature engineering, training, it is a track mode. So running DVC retro reruns only the stages that have changed. So critically, the raw files which we were using were of 3.4 gigabytes of AI CSVs. So these all files are excluded from the Git and they are versioned separately. I also evaluated using the GFW API for the live data for the live data ingestion, but it was deprecated. So we moved to the direct CSV downloads where they are stable and quite reproducible. And the last thing was the CI pipeline, which runs automatically on every push to the dev branch. So replinting and PyTest across all 14 unit tests. So the branch protection rules were also set up, which I configured for this for the Scrum 23 part, which means nothing will merge to the main branch without a green CI continuous like CI run and peer review approval. So that's what the code base kept clean for throughout sprint one. So the next is risks. So throughout this sprint one, we maintain a risk register. So the top risk which we faced were the data quality, specifically constructing the corrected hard negative data set. It's flagged high probability, high impact with the mitigation already in the backlog as the first ML task. For an from an MLOps perspective, the second task I am watching is the environment and drift as we add SAR computer vision dependencies. That's why the that's why the Docker setup is already containerized and ready to extend. So for the sprint two, the we have planned to work in three parallel domains. So we will be working on the ML part, which includes hard negative, corrected feature graph, SAR computer vision pipeline, and XGBoost risk score. Then the next part will be full stack for that, connecting the real world model to API, then delivering dashboard version 1, and for the MLOps part, AVC tracking for SAR imagery, proper updates for CV dependencies, and infrastructure guide for the pipeline. It is fully documented. For the sprint one, the this is the foundation for our entire project. So the gap detector is listed and stable. The feature engineering pipeline needs the negative class corrected. So the evaluate module is already reusable across all future trends. So coming to the last part, the key takeaways. So the first was proof of concept pipeline works end to end. The fast fail finding is a strength. Means we from the sprint one, we know exactly what we want to fix for the sprint two and the reason behind it. And the code base, the infrastructure and the tooling are all built in for the sprint two part. So yeah, thanks for watching, and we have given full access to notebooks, metrics reports, and feature catalog. They all are on GitHub. Yeah, and thank you.